ball A is dropped from rest from a building of height h at the exact same time that ball B is thrown up vertically. When they collide in midair, ball A has triple the speed of ball B. And this is an illustration of what happens. If the collision occurs at height h above the ground, what is the ratio of the height h over the total height, big H? So we have a condition that we need to satisfy here, which basically says that the final velocity of A must be equal to 3 times the final velocity of B. And in this case, the final velocity of the balls is their velocity when they collide. And A is negative because I have set up a coordinate system like this, where upwards is the positive y direction. So the final velocity of A will be negative since it's falling downwards, and B is thrown upwards, so it would be positive. I can arrange this to say that the final velocity of A is equal to negative 3 times the final velocity of B. So that's the condition that we need to satisfy here. Now, after that, we can use our kinematic equations to write some equations that we can use to solve for this condition. The first one that we're going to use says that the displacement, or change in x, is equal to the initial velocity times the time plus 1/2 times the acceleration times the time squared. Let's first apply this to ball A. In this case, ball A is equal to the change in displacement, or change of position of ball A, is equal to the initial velocity of A times the time minus 1/2 gt squared, where g is the acceleration, and the acceleration is minus g, so this whole term turns negative. And the initial velocity of A is equal to 0 because it is dropped from rest. So if I get rid of all of that, this whole part of the equation can be neglected. So the displacement of A, the displacement of ball A, is simply going to be equal to minus 1/2 gt squared. And now if you look in the diagram at the displacement of ball A, you'll notice that it is h minus h. So let's say displacement of ball A is also equal to h minus h. This is purely from the diagram. It's the big height, the total height, minus the height at the collision, and that gives us this segment here. And again, this is negative because we've established upwards to be the positive direction, and it's falling downwards, so this whole expression will be negative. So negative h minus h is equal to minus 1/2 gt squared. Negatives cancel, and you get that the total height is equal to 1/2 gt squared plus the height at the collision, which we have to calculate for using another set of equations that we're going to derive. So I'm going to rewrite this. Total height is equal to 1/2 gt squared plus the height at collision, h. And we need to find a way to calculate the height at the collision, h. Now we can use this equation again to figure out the displacement of B. So first up, the displacement of B is going to be positive h, since that is its displacement before the collision. And then we can use this kinematic equation again, saying that the displacement of ball B is equal to the initial velocity of B times the time minus 1/2 gt squared. And we actually don't know what this is, but let me rearrange this to say that the little height, the height at the collision, again, we can substitute that in here, is equal to the initial velocity of B, initial vertical velocity, it's launched upwards, minus 1/2 gt squared. So that gives us the expression for the height at the collision, but we don't know what the initial velocity for B is. And that's where this equation comes in handy. This one down here, which says that the final velocity is equal to the initial velocity plus an acceleration times the time. We can apply this to the velocity of b. In this case, the final velocity of b, which is the velocity at the collision, is going to be equal to the initial velocity of b plus 1/2 times the acceleration times the time. In this case, the acceleration is minus g, so it's going to be minus gt. And we get this expression. Now, if we look back at this condition we need to satisfy, we can multiply both sides by -3 to get minus 3 times the velocity of ball B at the collision is equal to minus 3 times the initial velocity of B minus gt. And looking back at this definition, we see that that is equal to the velocity of ball A during the collision. And that is going to be equal to minus 3 is the initial velocity of B plus 3 gt. And I just simply distributed here. So if I erase this to make some more room, oops, it's a little too much. Just erase this part. We can figure out what the final velocity of A is too. Again, we can use this kinematic equation. So the final velocity of A is equal to the initial velocity of A, which we've established is 0 since it is dropped from rest. So this whole part can be neglected. So it's simply equal to the acceleration times the time, which in this case, the acceleration is negative g. And of course, we multiply by t. So then we can substitute this back in to get minus gt is equal to negative 3, it's a bad negative sign, minus 3 times the initial velocity of ball B plus 3 gt. And from here is just the simple matter of solving for the initial velocity of B. So from here, rearranging, we get that minus 4 gt is equal to minus 3 times the initial velocity of B. Negatives cancel, so and solving for the initial velocity of ball B, we get that the initial velocity of ball B is equal to 4 gt over 3. And that's the expression we're going to use. So the initial velocity of ball B is going to be equal to 4 gt over 3. And we can plug this expression back in to figure out the little height, h. I'm going to plug that back in. So h becomes 4 gt over 3 times t, don't forget about this t, minus 1/2 gt squared, which becomes 4 over 3 gt squared minus 1/2 gt squared. And this will give you 5 gt squared over 6, or 5/6 gt squared. So after evaluating everything here, we get that the height, little h, the height at collision is equal to 5 times gt squared over 6. So that's the first part. Now we can plug this back into this, to the other equation up here. We can plug it back into this equation to help us solve for the second part. So actually we can also erase that. So h equals 5 gt squared over 6. Now we plug this back into this equation to get that the total height h is equal to 1/2 gt squared plus little h, which we substitute back in, which becomes plus 5 gt squared, 5/6 gt squared. And this should give the total height of 4 gt squared over 3, pretty sure. So that is another quantity that we have solved for. So the total height is equal to 4/3 gt squared, or 4 gt squared over 3. And now we have the two quantities that we need. So now we just need to solve for the ratio of the height at collision over the total height. So this becomes 5/6 gt squared over 4/3 gt squared. Gt squared cancels out, so we don't need to solve for the time. This gives us 5/6 over 4/3. And now we just simply simplify this, and this becomes 5/8. So the ratio of the height at the collision over the total height is equal to 5/8 for this problem. And that is how you would solve for this problem here.